The goal of today's trig workshop is to take what we learned about trig in our previous couple of workshops, which were mostly about trigonometry on the unit circle, and just expand our minds a little bit to circles that have a larger radius. So not just a radius of 1, but maybe a radius of 17 or something, right? And when we do that, the typical way in which we conceptualize this, instead of thinking about our triangles being drawn inside the unit circle, we just think of them as being triangles. So I want to go through these first couple of points real quick just by refreshing your memory on things that you probably remember from high school geometry. First of all, when I say a right triangle, what do I mean by a right triangle? What makes the triangle I just drew up here look like a right triangle? It has a right angle in it. So denote that by that little square. This is 90 degrees, or actually we don't like to use degrees in our class. How many radians is there in a 90-degree angle? Pi over 2. Pi over 2 radians. Because on the unit circle, if I walk a quarter of the way around, I have walked a distance, an arc length of pi over 2 along the circumference of my circle. Okay, so that's what makes this a right triangle. It has that right angle over there. Now let's suppose that I happen to know, and I'm gonna stick with degrees here for a minute. I hope you'll forgive me. Let's suppose that I happen to know that the measure of this angle over here is 35 degrees. How would I figure out what the measure of this angle is?
You would add those two and then subtract by 180.
Subtract by 180, right? Because we have this theorem from high school geometry that says that, so give me the warrant for that.
Triangle.
Yeah, so how do I know, like, what's the general statement that you used to make that calculation? What do we always know is true?
All triangles are 180 degrees.
All triangles, I feel like pushing back on that statement, but maybe I will in a minute. All triangles have a total, so we have to add them all together to get that 180 degrees, total angle sum, interior angle sum of 180 degrees. Or how many radians? Pi radians. Yep. Okay, right. Maybe now is not the right time for me to push back on this. This is, in some cases, not true, but in all the cases that we care about right now, is true. Yeah, remind me about that some other day, maybe. So if I want to know what this missing angle is, I just need to know what am I missing? How many degrees am I missing in my triangle? If I've already accounted for 90 plus 35, that's 125. 90 plus 35, those are both degrees, plus however many degrees I'm missing here needs to equal 180. Whoops. And so I'll simplify out the left-hand side, 125. I'm going to suppress my units, and then just subtract 125 from both sides to get 55 degrees. Okay, so that covers the first topic that I wanted to do. What relationship exists in a right triangle between all three of its angles? Then, at least in all the cases, we're going to talk about the interior angles all add up to 180 degrees or pi radians. Okay, so that handles the angles question. What about the lengths of the sides? I'm going to forget for the moment that we have labels on my angles. And we'll just say, suppose that I know the lengths of two of my sides. Suppose, say, that I know that this side of my triangle is 15 units long, whatever units we like. Let's just make them arbitrary for right now. And then we suppose that, wait, do I want to, yeah, 15. And then suppose that I know that this side has a length of 9. Pythagorean Theorem. That's the warrant for this that relates the three side lengths of a right triangle together. And what is the Pythagorean Theorem? What does it say? Yeah. So that's one of those formulas that's right up there with y equals mx plus b, or x equals minus b plus or minus the square root of b squared minus 4ac over 2a. This is right up there in terms of the formulas that people get drilled into their memory by high school mathematics, right? A squared plus b squared equals c squared. And so what are a, b, and c in this diagram?
The sides of the triangle.
Right. But there's a difference in this formula between the a's and the b's, which are on one side, and the c, which is on the other side. So how do I know which needs to be which?
C is the hypotenuse.
C is the hypotenuse, and what does hypotenuse mean?
Across the right angle.
Yeah. So C is the length of the hypotenuse, which is opposite the right angle. That's what hypotenuse means. Great. Hypotenuse, which is opposite the right angle, the 90-degree angle, or the pi over 2 radian angle, right? And then the other two, A and B, are what we call legs, the other two sides. And clearly the A and the B are interchangeable. It doesn't matter which one of these is A and which one of them is B, because we're adding the two squares together, and addition is commutative anyway. Right? So it doesn't matter which one of these legs is the A, which one is the B. As long as we're separating the legs from the hypotenuse, we're okay. Okay, so let's call this A, maybe. And so I'll get an equation, a squared plus 9 squared equals 15 squared. And that gives me enough information algebraically to then solve for A. 15 squared is 225. 9 squared is 81. And so I'll subtract 81 from both sides. If I subtract 81 from 225, I get 144. And when I take the square root, I get plus or minus 12. But why do I not care this time? Yeah. We want this to be the length of a side of a triangle, and we'll do the kind of geometry where all of our lengths are non-negative. Right? So A equals 12, and we're good. Right. So
what would it mean if it was negative?
it would mean we're doing a different kind of geometry. I'm kind of, geometry is kind of one of my research interests, and so I can say way too much about this kind of thing. I will just say, suffice to say that the kind of geometry that is the most practically and intuitively useful is the kind in which lengths are non-negative.
What would a shape look like if there?
The Pythagorean Theorem is another one of those things, just like the interior angle sum thing, that we can actually make not true in some kinds of geometry. But at least in the kind of geometry we do, and this here, spoiler alert, the geometry that we do when all of our figures are drawn on flat paper, interior angles are going to sum to 180 degrees, and the Pythagorean Theorem is going to hold. And the Pythagorean Theorem has a million proofs, but my favorite proofs of the Pythagorean Theorem are these really sort of kinematic ones. Where did that go? If you fill up the top two squares in this diagram with water, right, then the area of those squares is going to be the side length of each one squared. So this square would have A times A square feet of water in it. This one would have B times B, right? And then if we let those squares drain into the bottom square, it exactly fills up the bottom square. And I don't know how to get this thing to run its animation again. There we go. Right. So the same amount of water is in the sum of the top two squares as we get to the bottom. And people have actually built like physical models of this with the squares on a giant wheel and a bunch of water in there. And you turn it and you say, oh, it exactly fills up the bottom. But this is one of those statements that's been proven in a million ways over the years by various mathematicians. And so really the most interesting question that we have today is, okay, we know how to get all the sides to relate to one another. We know how to get all the angles to relate to one another. How do we start mixing and matching? Right? How can I take two of the side lengths and tell me one of the angles? That's actually a little bit harder question that we're going to have to wait until later into our trigonometry unit to do. So for today, we're going to do it this way. Today we want to be able to take one side and one angle and use that data to predict another side. And here's the key to that, right? When we measure our angles in radians, what kind of units? Do you remember when we talked about radians in our trigonometry workshop before? What kind of units are radians? Arc length over radius tells me a radian. And both arc length and radius are measurements of length. So if I divide one by the other, I get a length divided by a length, meters over meters, inches over inches, feet over feet. Those units just cancel. So radians are ratios of lengths, and therefore they're dimensionless. And that actually gives us a little bit of a clue as to how we might be able to do this, right? If I want to use one side and one angle to predict another side, what I might want to do is take this one side and divide it over here. So I'm doing pseudo-math for a minute here. But this is how we're going to use this. We're going to be able to, we're going to be able to do this using ratios. One angle is going to be able to be predicted by the ratio of one side length to another side length. So this is the point at which we go back to our last trig workshop, which let me find it in my notes here. I think it's this one. Nope, it's not this one. So the radian is the arc length divided by a radius. But we also learned about these two trigonometric ratios, which told me the ratio of the y-coordinate and the x-coordinate of the corresponding point on the unit circle divided by the radius. And we called those ratios the sine and the cosine, respectively, of the angle inside of my right triangle. So, way back then, we were able to ask, what's the sine of the angle pi over 6? And we found it by dividing the y-coordinate of this point, 1/2, divided by the radius of the circle, which also happened to be the hypotenuse of this right triangle, inscribed in the unit circle in this way. Right? So the sine was 1/2 divided by 1. 1/2. The cosine was the x-coordinate, square root of 3 over 2, divided by, again, the hypotenuse, which was the radius of the circle. So that's 1, right? Oops, this is getting away from me here. There, I'm going to put a stop right there, right? And so all we have to do to take this picture and apply it to other kinds of right triangles is we just have to think about what happens if this radius is different. Right? If the radius of my circle is different, that makes the hypotenuse of my right triangle different. But all of this definition over here carries over. Right? So let's go to one of our example problems, and then I'm going to turn you loose on the rest of them. For example, if we're asked for a right triangle where one of its non-right angles satisfies sine of that angle is 3 over 5, how could I draw a triangle in which that holds? I'm going to kind of just draw a generic triangle for a second without respect for scale. My right angle is over here in the bottom right-hand corner. Right? And if I want an angle which has a sine, by the way, this angle here is a Greek letter, alpha. Often to keep stuff straight, in equations and expressions involving both lengths and angles, very often we'll use Greek letters for the angles and English letters, Latin letters for lengths. So just as a way of keeping that straight, that's a convention mathematicians often use, just to give us a cue to tell angles apart from lengths. So if we're saying that the sine of alpha is 3 over 5, remembering that the sine was nothing more than the ratio of the y-coordinate to the hypotenuse, the radius of my circle, where would I find a 3 and a 5 in this diagram if I, for example, place my angle over here? Let's just imagine. Yeah, so I'm just going to imagine that there's a big circle. See if I can do this. I'm not going to do this particularly well. So I just imagine that this is inside of my unit circle. But it's not really my unit circle anymore, because what's the radius of my circle going to be? 5. So now the radius of my circle is 5, and where do I find on here the radius? It's the hypotenuse. So instead of radius, we're going to think of that denominator there as the hypotenuse of my right triangle, so that I don't have to remember to draw a big circle around my triangle every time. Right? So we're going to think of that 5 as being the hypotenuse. And then what about 3? 3 was supposed to be the y-coordinate in the unit circle for the sine. Right? Well, if I don't have a coordinate system on here, where do I find that 3?
Across the angle.
Opposite from my alpha. So this side of my right triangle is where I'm going to find the 3. This is the side opposite to my alpha. Opposite to alpha. And so this side right here, 3. And there is a triangle with an angle in it that satisfies sine of alpha equals 3 over 5. Okay, so here's a follow-up question. In this same triangle, what would the cosine of alpha be? How do you know?
The missing angle.
I need to find, well, yeah, so I can look at this a couple ways. So cosine, remember, was the x-coordinate divided by the radius. We decided radius was
5.
hypotenuse, is right, the same as the hypotenuse of my right triangle. But then what role would the x-coordinate play?
Adjacent.
It would be, yeah, what we call the side that's adjacent to alpha, right? It's the side of the right triangle which is not a hypotenuse, but which is also not opposite to my angle. It's contained as part of my angle. It makes up one of the right rays that defines my angle alpha. And so I would need to find what is the length of that side. And for that, I would use the Pythagorean Theorem. A squared plus 3 squared equals 5 squared. A squared plus 9 equals 25. A squared is 16. So A is 4. And so the cosine of alpha would be how much? 4 over 5. Done. Great. Okay. And so what this does is it gives us a new way of understanding the definition for sine and cosine. And the way to do it is to think about the right triangles that have these angles in them. And for a right triangle, the sine of one of its non-right angles is the length of its opposite side divided by the length of the hypotenuse. And the cosine of that angle is the length of its adjacent side divided by the length of its hypotenuse. Right? And this is the beginning of an acronym that, if you've had trigonometry before, will be instantly recognizable. Sine is opposite over hypotenuse. Cosine is adjacent over hypotenuse. Yeah, we haven't talked about tangent yet, but we will. And maybe we can get a preview of that for today. Because when you take the first letters of these, S-O-H, C-A-H, it begins to build probably the acronym that most people who've taken trigonometry have had drilled. And another one of those things that just gets beaten into your heads after a while. Let's do the very last one of these. What happens if I don't know the hypotenuse? What if I want to use the two legs instead to form a ratio? SOHCAHTOA. Sine is the opposite length over the hypotenuse. Cosine is the adjacent length of the hypotenuse. And tangent is the opposite over the adjacent. But also, and this is the last thing I'll say before we have about 10 minutes to work the rest of the problems on this exercise. The other way to think about this is what's the relationship between sine and cosine in tangent? If I want to take these quantities and combine them together in a way that makes the hypotenuse cancel, how could I do it? Maybe make a little space here. Yeah. If I divide sine over cosine, opposite over hypotenuse divided by adjacent over hypotenuse, then the hypotenuses do cancel, I get opposite over adjacent. And so what that tells me is that the tangent of an angle is nothing more than the sine of that angle divided by the cosine of that angle.